Did everybody have an opportunity to get around and see the whole complex yet? How many have stretched their legs? Been around? It's a big facility. It's one of the largest in Cleveland area, and it's user-friendly. Holiday Inn, we've been working with them for about 3 years for this conference. Program chair for this year, and it's our pleasure to take this side over in this room to do some intros, and we're going to have some real gifted talent here. Bryan down front here, he's really all fired up. He brought his rollerblade in here, and he's going to go firing up into outer space with some advanced propulsion. Bryan is ready and eager, and we want to make sure with the lighting sequence, because they have 2 panels, one in the back and one in the front, and we'll try and get that so you're not going to sleep in 10 minutes, right, Bryan? We throw up the firecrackers if they start to go to sleep. And chart, you got an appointment to go to the dentist after this, right, or something like that. Well, Bryan comes to us from Mass Lewis, and he's been a real supporter of us over the years, and he's in the engineering group in this propulsion unit. He spoke to many of our conferences at MSDC, and he's been a loyal, strong supporter of the Cleveland area. He's always come out to civic groups and talk. And to beat the drum to him, he's really been a real helper with us and a co-supporter of the movement here, and supports us in the space development. With that, we're going to have Bryan come forward. He's going to do some slides. More people are coming in. We'll try to keep it as fast moving as we can. What we want to do, for his benefit, go about 45 minutes, go about 10 minutes with the questions and answers, and if you want to talk to him more, go out in the hallway. Let the next speaker move in so we have a great opportunity. On the other side, we have small disadvantaged business going on. There are some real important people over there. If you're interested in that, if you didn't know, that's in the Broadview Heights room. This will be the main thrust for this afternoon. There'll be several tracks running in this room, so if you want a small disadvantage, it's over there. Bryan, we're going to bring you forward here, and I'll probably get nervous and mispronounce your name, so I'm going to go through here. Palaszewski, is that right? Close enough? Okay. Bryan's going to come forward, and I'm going to get off the stage here and let him. He's a free floater. He likes to work out in front where he's with the people. He'll probably be coming up and down here, but he doesn't like a podium. So, Bryan, we're going to let you rock and roll over here. This is Cleveland, don't forget. Now, rock and roll, Bryan. Bryan Palaszewski.
Hello, everybody. I'm here to talk to you about a very small portion of advanced propulsion. If I talk about everything that's going on in the country in any great detail, it would take years. So I'll give you a relatively tight presentation that talks about some of the more major areas in advanced propulsion that are going on in the country, both with regard to the large government assisted programs and also some of the more smaller commercial tech programs. Just to show you where we're going, I'll talk first about why are we interested in propulsion, who cares about it, and then I'll talk about some of the different areas in advanced propulsion, the very, very near-term areas which are more related to onboard propulsion, electric propulsion, and then some of the things on reusable launch vehicles, and then the far term, which is a very rich area for research with universities and the government and industry, and then some conclusions. Now, you can see that when you look at spaceflight, almost everything that you see related to spaceflight has propulsion related to it in some way. Like, for example, launch vehicles, about maybe 80 to 90% of the launch mass, when the gross liftoff weight of the vehicle leaving the ground, is propulsion or propulsion related. You've got launch vehicles, upper stages that are taken into orbit by these launch vehicles, like the space shuttle and others. Satellites and spacecraft, all of them use some type of propulsion. It may not be very extensive in some cases, but it may be a driver in terms of its life in many cases. Propulsion is also important in terms of reducing costs. If we have 90% of the mass of the vehicle, often that relates to a lot of operational issues that are related to cost and maintenance. And if we can get these kinds of things under control, maintainable systems and operable systems, it significantly reduce the cost of space flight. So propulsion is very important with regard to that. And of course, there are other important issues like safety, maybe using safer propellants in the future, and also things like accessibility, launch environment, vehicle resiliency. These are all driven pretty much by the launch vehicle or the propulsion system on board a spacecraft. And not to be overlooked, even though this is an international space development conference, we're pretty proud about what we're doing in the United States, and there's an importance in national preeminence that's demonstrated by our launch capability. Going all the way back to Sputnik, when Braun got livid at the government for allowing the Russians to have the first launch. National preeminence even comes in today with regard to commercialization of different abilities and satellites and all that, and competition with the Chinese, Russians, and all the other commercial launch people in the world. Of course, European Space Agency. Now, one of the big areas, and what I'll do first is focus on some of the smaller propulsion elements, but they may be small in terms of physical volume, but they're enormously important in terms of expense and cost and competitiveness for the United States. Onboard propulsion is a major area that's being worked on at NASA Lewis and throughout the nation with different spacecraft propulsion capabilities in terms of drag makeup for International Space Station, RCS for launch vehicles, the orbit insertion and orbit control for lower orbit satellites, and of course for geosynchronous satellites, getting the propulsion to get it up there and maintain it in its orbit over its 15 or 20 year life. And one of the areas that Lewis is helping with in terms of these type of propellants for these type of satellites is primarily chemical and electric systems. Electric being arc jets, and ion propulsion and chemical propulsion being higher temperature rockets that have longer life and or higher specific impulse or miles per gallon for the rocket. And what we're doing that with is by doing tech transfer, cooperative agreements, and outreaches to different industry and university systems to help them use the kind of technologies that have been worked on for the last 20 or 30 years and really get them into systems to save billions of dollars for commercial satellite systems over their lifetime. So one of the areas that has been very, very successful is a dual mode rocket engine. Dual mode essentially uses hydrazine and nitrogen tetroxide as its fuel and oxidizer, and then uses hydrazine as its RCS propellant, so there's a commonality between the tankage of the main propulsion system and its reaction control system. And this type of cooperative agreement between TRW and Lewis allowed the demonstration of an engine using a high temperature rhenium combustion combustor technology. It's a very, very high temperature chamber that allows us to operate at approximately 20 seconds higher than traditional NTO, MMH, or NTO hydrazine type systems. So we've got a lot of specific impulse increase. And even though 20 seconds may not seem like a large increase, it's enormous in terms of the lifetime of a satellite that's on orbit. That extra 20 seconds might be able to give us another 2 or 3 years of life on orbit, or maybe more. And also, this type of apogee engine will allow TRW to win an international competition on what type of propulsion would go on board these satellites and which satellites would have the longer life. So it really helps American competitiveness by transferring this type of technology. Another type of rocket engine technology, it's a little, this is electric propulsion. It's called an arc jet. The arc jet has a very, very intense high temperature electrodes here with a plasma that's generated about 20,000 Kelvin, and the propellant is heated by this 20,000 Kelvin plasma arc and flows through the nozzle at extremely high velocity, and it has a performance typical of that NTO MMH system we were talking about before, about 300 or 308 seconds. We can about double that specific impulse, and this adds even more to the lifetime of satellites and allows us to do very, very small spacecraft propulsion for orbit raising, and allows us to get very, very compact systems so we can launch perhaps multiple satellites on one rocket and make spacecraft smaller and give them more lifetime. Again, all these different technologies, they're all things that are really helping to generate billions of dollars for America's commercial satellite system. So I can't stress enough the interest in that. And another aspect that we work on at Lewis with our industry partners is some work we did integrating the ArcJet into a simulated satellite in one of our factory chambers. So some of the engineers looking at the sensor where they were looking at the different electrical emissions of these different thrusters and making sure that these electrical emissions did not disturb the other electrical systems on board the spacecraft or did not provide or did not enhance some of the spacecraft charging that might go on and significantly damage the spacecraft. So these are the other kind of cooperative ventures that we do with industry. Now, moving away from Earth orbit, let's go a little bit and talk about other types of electric propulsion. Solar electric propulsion have the ability to do some really exciting things by going to comets a lot faster, maybe about 50% shorter time. So instead of taking 6 years to get to Vesta, it only takes about 3 years. So these are really important in terms of costs for the spacecraft and costs for our planetary program. Also, these smaller electric propulsion systems, about 5 kilowatt power level, can allow us to do light-sat spacecraft launched on relatively small launch vehicles. And in the old days, when we were thinking about sending electric propulsion systems to Halley's Comet, we had about 30 or 60 kilowatts of power on board the spacecraft, and we needed a relatively large launch vehicle like Space Shuttle to do these missions. Now we're thinking about these smaller systems because our administrator, Dan Golden, is asking us to be faster, better, and cheaper, and stretch our minds a little bit about how we can make things more compact and more cost-effective for planetary exploration. And just another simple example of the kind of small spacecraft that we can do. We can do a near-Earth asteroid rendezvous, which is considered one of the most demanding propulsion jobs off of a Pegasus launch vehicle. Very, very small payload. You see the total spacecraft mass of 115 kilograms, whereas in the older days we used to think of many tons of spacecraft being sent to a near Earth asteroid in order to accommodate all the propulsion requirements. So electric propulsion, with ion propulsion, can really get us significant savings in terms of mass and allow these small spacecraft to fly on relatively inexpensive launch vehicles. Now let's move away from electric propulsion. Let's talk a little bit about single-stage orbit. This has been a very exciting prospect for about 50 years. And now we're finally starting to think more seriously about these kind of technologies. And the Air Force and NASA are working very closely with industry partners to try to develop what will hopefully be the first single-stage orbit vehicle, or an X vehicle that will lead to single-stage orbit. Now, one of the things that has frustrated single-stage orbit in the past is these kind of things, where people have said, oh, there's an economical advantage by single-stage orbit. You're not throwing pieces away, and we can reuse the whole vehicle, and it's simple operationally. But sometimes we made errors in our technology assumptions, but maybe now we'll be able to fix those errors, and we have some better technologies of lighter weight engines and lighter weight tankage to do these kind of things. And of course, ECY is one of the proposed vehicles to do that. This is a system that's being proposed by Donald Douglas, and now with the X-33 program, there's a further development of that program. NASA is providing some small funding on the order of $1 billion over 5 years, and the industry is theoretically going to be providing most of the investment to develop that vehicle. So it's a very unique area where NASA is doing a lot more hands-off, or theoretically doing a lot more hands-off, and allowing the industry to find the vehicle that they want for a single-stage orbit. Now, this is just a simple chart to talk about what kind of mass fractions and what kind of propulsion problems we've had in the past that have prevented some of the single-stage orbit vehicles, and see that for the available materials, this is the kind of mass fraction we needed in order to do single-stage orbit with our older materials and older engine designs. And this is what we could have done with the materials that existed before the space shuttle system was defined. And then as time went on, the 75-85 regime, we said, oh, now we've got a little better materials and better engines, and we can get up to about this point. We need to get it to about this point, but we can only get about here. And now our thinking is that we're just on the razor's edge of getting to a single-stage orbit type vehicle. So we think that a lot of these systems have progressed far enough that we can actually do this in a reasonable time. Now with the X-33 and 34 programs, NASA's, again, tried to develop advanced technology demonstrators with 3 different contractor teams. There are 3 contracts in place that are looking at some of the technologies to develop and successfully build a demonstrator of a single-stage orbit vehicle. The demonstrator itself will only demonstrate technologies. It will not get single-stage orbit, but it will go a large fraction of the way to orbit. But it will be able to, what they use the term, it will be traceable to a ultimate single-stage orbit vehicle. So after this demonstrator program is over, in about 5 years, hopefully we'll have a vehicle that we can evolve into a single-stage orbit vehicle. Now the X-34 is a little different animal, and it's been in the newspaper quite a bit in space news, and I guess the name is going to be changed so that it does not appear to be an X vehicle, but this is really a small booster that Orbital Science and Rockwell will be building with NASA for more commercial type missions, not really an X vehicle as such. Now most of the traditional designs for single stage orbit have focused really on rocket propulsion. There was a study conducted by NASA ended about 1994 called the Access to Space Study, where they looked at systems like rockets, and then they looked at air-breathing vehicles, and they paid some lip service to what are called combined cycle vehicles, which take what some people perceive as the advantages of air breathers and the advantages of rockets and put them together. And it's not clear that both of the advantages of both will be put into the ultimate vehicle that's made, but there are a lot of people who have a lot of strong opinions about whether or not the combined cycle vehicle might work the best. This is just a chart that talks about what kind of specific impulse an air-breathing type vehicle might be able to develop, or a combined cycle vehicle might be able to develop versus a rocket. You see this line down along the bottom is a very high specific impulse rocket, which is a little under 500 seconds, 460. And the theory is, and if we use a rocket or some sort of rocket ejector type system on this part of the flight, go over to ramjet and scramjet for the air-breathing portion of the flight, and then drop down back to a pure rocket. This type of system would be the most efficient based on some of the studies that have been done for single-stage orbit type vehicle. And there are a number of NASA centers who are trying to plan a small experiment, maybe to fly on the X-34 to demonstrate some of these air-breathing rocket type concept, or rocket-based combined cycle type concept. So there are some other different types of other than pure rockets that are being considered. Now, one of the things that's been used in some of these rocket-based combined cycle systems is what's called gel propellant. Gel propellants essentially are ultimately safer propellants because they are gel. They have a smaller spill radius, and potentially in some cases they can have higher performance by adding metal particles. You see some of the work that we've done at NASA Lewis. We've looked at oxygen, hydrogen, aluminum type systems where we gel hydrogen with aluminum particles, and we've also done some combustion work with oxygen, hydrocarbon, aluminum type systems. And the military is particularly interested in these gel storable type propellants, nitrogen tetroxide, monomethyl hydrazine with either carbon or aluminum added. They're looking more at the military type systems, but they're also looking at these for a combined cycle sort of system for advanced missiles. So there are some advantages in there for the military as well as for NASA missions. And just to show you what one of the benefits of higher density propellants might be, if we were to replace the solid rocket boosters on the space shuttle with a liquid rocket booster, see that the size of the SRB is about here, and a liquid rocket booster that did not use gel propellants gives you a booster length of about A, and a metallized booster drops this down quite a bit and reduces the length. And if we allow this length to come up to the same level as the solid rocket booster, we get about 14% payload increase to a low Earth orbit. And then if we allow the LRB to increase in length by about 3 feet, we get about 60,000 pounds of LEO instead of the 50,000 pounds per shuttle now. And if we allow it to go 13 feet, we get about 70,000 pounds. Or we can trade that for a 1 foot increase in diameter. So there are some advantages to these high density propellants in some cases. And no presentation of rocket propulsion would be complete without a smoke and fire photo. And this is oxygen RP1 aluminum at 55% metal loading fired at NASA Lewis. You can see the plume is very intense white. That's because the combusting metal particles in the plume. And this is a relatively small engine. It essentially fits in my hand. And it's just a glory picture for us with some wonderful testing conditions. Now, some other areas in the Air Force, the Phillips Lab at Edwards Air Force Base are looking at some other types of additives for propellants, something called high energy density materials, which are in some cases, and I should say one example of those is a hydrocarbon that has a stringed ring. Essentially, it adds a little more energy to the chemical bonds, and by taking out the regular hydrocarbon fuel and adding these additives, we can increase the performance of rocket systems by maybe several hundred or several thousand pounds more into lower orbit for some cases. And there are a lot of exciting possibilities with these type of propellants. We're cooperating with the Air Force right now on some work with solid cryogenic propellants, and also doing some work with a small company named Orbitech in Wisconsin, Madison, Wisconsin. And they were looking at systems that essentially have solid oxygen or solid methane type propellants. And the purpose of these solid cryogens is to store some of these unusual atoms. And if we store these atoms, which are relatively unstable, they like to recombine with themselves and go back to a rest state. If we can take these atoms and dope them, if you will, into a solid cryogen, we might be able to get a higher energy type of propellant. And one of the ultimate examples of that is atoms of hydrogen in solid hydrogen, which gives us some interesting performance levels. For 15% load of atoms of hydrogen in solid hydrogen, we can get about 750 seconds specific impulse. And if we go up to about 50%, we can get about 1,200 seconds specific impulse. Now, the level that we think we can do with current physics is at about 5%. So we have about a factor of 3 to go in terms of storage capacity to get to this level. But just as an example, you can see that gross liftoff weight of this vehicle can be reduced from about 1,900 metric tons to about half that, less than about 750 metric tons or 800 metric tons. So there's a lot of leverage, especially if we can get to these unusually high levels, which you can't even conceive of doing right now. But you can see that there's a tremendous advantage to some of these systems. But we think that we can make some of these first steps and dope maybe 5% of these atoms into this system and maybe get their gross liftoff weight reduced to a level maybe about this level. So there are some potential important advantages to this for the long term as well as the near term. One of the things we found with atomic hydrogen, though, when we try to store it, is we get to a certain level, and all of a sudden, all this energy gets released, and the number of atoms just drops to almost nothing. And then the energy builds back up again and drops down, and then builds up to another level, and then it starts to drop off. And a lot of this has to do with the fact that when the atoms are stored in the solid hydrogen, there's a radiation source that's creating the atoms as you go along, and it's actually damaging the crystalline structure of the solid hydrogen. And we haven't found a good way to do that yet, although we're pursuing some different ways using molecular beams or some other type of system. And if somebody wants to get completely fanciful, we can talk about nanotechnology, which is, of course, still in its infancy, but it has a lot of potential, especially if we can put little factories like this on a chip. See the acme with smokestacks and all this, and you know, it's sort of a good thought experiment to do. Is that, gee, how small can we get factories that can make atoms or manipulate atoms? And if we could get down to this kind of level, then we might be able to have some hope to deposit small amounts of energy and actually form the atoms in situ inside the atomic hydrogen. It's a little bit out of the normal range. Pay homage to Eric Drexler for putting those kind of things together, creating those kind of ideas. Now, one of the other areas in NASA that's doing other advanced concepts is the Jet Propulsion Laboratory, which has over the years had a very good relationship with NASA Lewis in terms of doing these advanced concept studies. In fact, I used to work for JPL, so I used to do these kind of studies for them. Only about 6 years, so it wasn't very long. And what they've done is they've tried to focus these advanced propulsion concepts by a number of different areas, because we've had a lot of pressure in the budget to focus ideas on ideas that seem to make sense for a well-defined mission class and show good performance after 3 years of working on them, and of course using some environmental acceptance. Like, for example, in the old days with ion propulsion, we used to use things like mercury and cesium for the systems, and of course that contaminated all of our facilities and really caused us a lot of heartache in the future. Now, some of the examples of what JPL is doing in terms of advanced propulsion concepts right now is some of these solar electric propulsion missions for LEO to geo transfer using carbon-60 or buckyballs as propellant. There seems to be a good charge-to-mass ratio for a lot of these different unusual carbon atoms or collections of carbon atoms, and it seems like it has some benefit, although we haven't really demonstrated all that yet. Of course, planetary missions are also of great interest to JPL. Some of the very unusual piloted or cargo missions for Mars. You know, the word Mars doesn't appear here. You can see that in the big letters. That's what we're talking about. Nuclear electric propulsion, the megawatt class, is lying fallow right now. There's not a lot of investment in terms of those reactors, but if it ever does come back, we'll have some good ideas on how to get very efficient electric propulsion to use those high-power reactors. And of course, a fast Mars mission or interstellar missions. We have some work going on at Penn State in very long name anti-proton catalyzed microfission fusion. I'll show you what the looks like in a second. And of course, we're also looking at other types of micro spacecraft with other types of small pulse thrusters. I'm currently with antimatter, which is stuff of dreams, Star Trek, all that kind of stuff. And I've got my United Federation of Planets pin on, so we're all feeling good. Antimatter is not something that we can manipulate the way they do on Star Trek. They use it at 100% efficiency or so. Wow, that's pretty cool. Not too many machines we know operate at 100% efficiency. And what we've done is over the last few years, we've been doing some analysis of how we would use antimatter as a rocket propellant. And it seems like the kind of efficiencies we're coming up with are 1%, 0.5%, maybe less. And you know, we don't have a good design for using antimatter, but we're still thinking about it on a low level, very small level. antimatter is sort of a dirty word on NASA headquarters in some areas, so you have to sort of couch it in the right terms. Yeah, we're doing hydrogen research. It's true. Life's really tough. You're bureaucratic, justify it. But anyway, with antimatter, this is what we produce a year, 2 nanograms. And they think that if they improve the accelerators, they might be able to increase that by a factor of 100. And then storage of antiprotons, do that at about 2 picograms a year. Picograms, 10 to the 12 grams. Very small amount. It's not like clumps. 10 to the minus 12 grams. And this chart, this man-made efficient conversion of annihilation energy. Yes. Man-made high efficient. We haven't got it. We're trying. Very trying. Now, one of the ideas, or 2 of the ideas that Penn State and others with JPL have been thinking about in terms of propulsion are some rather ambitious ideas with antimatter. Now, the first one, this is a simpler one to explain, so I'll go with that one first. In the old days, in the 1960s or late 1950s, there was an idea called Orion, where we take little nuclear weapons and throw them out the back of rockets, and boom, we'd take the force from that explosion and use it to push the rocket along. And you've seen that in science fiction films and all that kind of stuff. They have a lot of exciting different ideas about how to use Orion type propulsion. Very brute force, but hey, if it works, why not? And the other idea, maybe, is if you have a laboratory module in a spacecraft and you have very long feathers, and you have canopy made of unobtainium or something, or unobtainium dioxide. And you take a little bitty fusion pellet that's helped along by antimatter, and you can take this blast wave and you can hopefully contain it enough and not destroy your canopy that's made of unobtainium dioxide. And your spacecraft will along. Now these explosions might go off, maybe every 1 second, maybe 20 a second. So it depends on how fast you wish to go to your target, or the planet, or whatever you're trying to get to. So these are just some preliminary concepts of how antimatter might be able to be used. Some of the others that we've come up with haven't been quite so successful. So we wanted to take a look at some of them. Anyway, just to show you where we've been, we've talked about propulsion, and I think it's important, and I hope I've convinced you that there are at least some areas of propulsion that are important for reducing costs, better safety, and getting some of the national preeminence back and making us more competitive in terms of spacecraft propulsion for very near-term things like satellites and spacecraft. And we've got some very exciting reusable launch vehicle programs underway with NASA's assistance, although the contractor organizations in the industry are the ones who are really leading this program. NASA's trying to do a little more hands-off on that to allow the industry to build a real vehicle. And of course, I've shown you just a smattering of some of the advanced concepts. Every year, JPL has an advanced concepts workshop that publishes a 3-inch thick proceedings, and we could just go on for days. So I'll stop soon. And of course, beyond some of the advanced concepts I've shown you, there'll be a gentleman here also from NASA Lewis who will talk about other areas that are more speculative, but potentially can give us something that's propulsion without propellant. And he's going to talk about that, I believe it's on Saturday or Friday. Sorry. Anyway, the last thing, of course, the sales pitch. Send money. There's lots of things we can work on, and we're trying to help the industry be more competitive internationally, and we're trying to do a little bit of work on the very, very advanced stuff so that when the next revolution comes around, we'll be ready to do some neat things with advanced propulsion. Thank you very much.
I had done some looking into these ideas, like the JPL Foundation, and possible missions to focus the on the transportation event, 558. I was wondering if you had gotten involved in any of these studies and if you knew about the consensus on which propulsion method is best.
Well, Tau was conceived originally as a very good candidate for high-power nuclear electric propulsion. I believe a 4 to 10 megawatt reactor. You could do that mission in about, I guess it was 50 years. Because they wanted to limit the lifetime of the mission to something that a researcher could live through.
So start with the integration.
I started 8th grade, and then you're okay.
On the metallites gel, does that bump up the amount of oxygen needed for the color as well?
Actually,
Are you actually burning the aluminum, or is it just being ejected out?
oh no, you actually are combusting the aluminum. In the experiments that have been done in industry and NASA, we found that right now it's relatively inefficient. It's only about 70% of the metal actually gets combusted at the maximum. Lower levels, about like 60% combusted. Actually, the mixture ratio goes down, so you actually use less oxidizer because in a lot of the cases, because the metal provides so much more density. When you look at the mixture ratio, it actually shifts down. So the fuel tank actually increases in size, but the density is going up, so it shrinks. And we can sit a little bit.
How important it is that was told you had the boilerplate, that I didn't tell you you had to adapt this one. He went through his presentation, so we got time.
I know I've been reading on the level that has a really good homepage. Is there any chance that perhaps the presentation that you're making about that could probably be on the homepage?
I'll talk. I don't have a homepage myself. I've been yeah. He does. I will talk to him and ask him if he can do that.
There's also, like, some of the things that, our part of the study and the references that we have in the past.
Sure.
And, that would be something.
Sure. I'll talk to Dave about that.
We have a question in the back. Can you stand up, please? I can't hear.
Yes, has any metal been bent on X-33 yet?
Let's see. Let me remind myself. On X-33, what they're doing is some smaller technology experiments. Like, for example, some of the work that I'm involved with in Lewis is working on gas-gas injectors. That is where we use gaseous oxygen and gaseous hydrogen instead of using liquid oxygen and gaseous hydrogen as you do in the SSME. And the theory with doing that is that you have a much lower turbine stress and other types of stress because you're operating at gas temperatures that are a lot easier to pump instead of pumping liquid oxygen around in the engine. So there's still liquid in the tank, but once you get it to the pre-burners, they vaporize it with a very high O to F combustor and then send it into the turbo machinery. So there's little technology experiments being done. It's not bending metal in terms of building a full-scale tank as yet, because the monies that have been provided to the contractors so far are for just those preliminary experiments. I guess it's like the first year or so they're involved in those smaller scale experiments that ultimately are scaled up to a larger X-33 demonstrator. So there are little pieces of metal in
Can you stand up, please?
Yeah, you mentioned something about this award-winning engine.
Yes.
Talking about TRW.
TRW.
Could you
Reading.
elaborate a little bit how that engine worked?
Okay.
And what type of, how efficient, you mentioned something like 98% efficiency.
Yeah. Let me go back to that, sure. See, the rhenium engine that TRW is working on is part of a series of technology demonstrations that have started back in like 1978, where actually JPL was doing rhenium type thrusters, and the 98% combustion efficiency is not so important as the very high ISP that you're developing. 98% efficiency is not really that difficult to develop in a chemical rocket because we've been doing it for so long. But the 328 seconds is really the important thing. Because what happens when we have that higher specific impulse, which is 10 to 20 seconds higher than the previous technology, the existing technology. You can reduce the size of the propulsion system, use a smaller launch vehicle to launch the same satellite, or put multiple satellites on board one launch vehicle instead of having only one satellite per launch vehicle. So that kind of flexibility in terms of not only the launch mass, but maybe extending the life of the vehicle on orbit. Because once you have this higher ISP, you can load more reaction control propellant on board the vehicle and extend its life for, say, like 10 years to 15 years. So there are all these different trade studies that they've done to show what the benefits are. And there's really tremendous leverage in just a little bit of specific impulse gain on these type of systems, because you're all the way on the end of the lever, so to speak. And the least little amount of ISP gain here gets you to smaller propulsion system to move it out to geo, smaller launch vehicle, to take it off the ground. So there's a tremendous leveraging effect that's enabled by that small increase in specific.
Two more questions though. About
Stand up, please.
which part of, what aspect did it actually win the competition or win some type of award? What aspect of this technology, and how far away from any kind of development and usability in spacecraft is this technology?
Okay, this is going to fly in 2 years, and so it's near term. I mean, it's not something 10 years away. You know, like I said, we've been working on this kind of technology since '79. And it's like, wow, it took a while, to get it to a point where the industry was pressured enough by competition from ESA, because ESA has a launch complex in French Guiana, which is only 3 degrees off the equator. And hey, you can get the geosynchronous orbit a lot easier, 3 degrees off the equator rather than 28.5 degrees. And that this is what they're talking about in terms of the international competition. It's whether or not this series of spacecraft would be launched on Ariane launch vehicles versus American launch vehicles, or whether the satellites would be launched on American launch vehicles or Ariane launch vehicles, or maybe even Chinese launch vehicles or Russian vehicles. So there's a tremendous leverage in terms of cost, in terms of improving the life of the vehicle. And it's very near term. Like I said, it's going to be flying very, very soon.
We had a question from somebody right there. Can you stand up, please? Speak loud.
Can you say a little more about first about these atomic hydrogen materials and like how do you make that? And secondly, you alluded to solid oxygen and solid methane, but you didn't say much more. I mean, what things were you planning on sticking inside the solid oxygen and solid
All right.
methane?
Let me show you one thing about the atomic hydrogen, and I'll talk to you about the oxygen and the methane. In this series of experiments that was done in Livermore, what they were doing was they're using the same materials that they're using for the fusion program. They're essentially taking deuterium, tritium, built in solid hydrogen, and they use the radiation from the decay of the tritium in order to form the atoms of hydrogen. So if you've got this little slushy ball, and you put it inside this detector, you'll see the radiation coming out, but they'll be forming atoms, and these atoms start to form inside the solid. And then when it gets to a certain level, the atoms release light. About 90% of the energy comes out as light, and 10% comes out thermally, at least from the measurements that have been done so far. So you're really using the decay of the tritium in order to create the atoms in the solid hydrogen. Now, with regard to the solid oxygen and methane, the reason we were primarily interested in the oxygen and the methane was as a precursor experiment to some of these other advanced propulsion systems that the Air Force is looking at. Too much propulsion. Si, senor. What happened was, because of budget reductions and things of that nature, we said, hey, if we could have a small company do some preliminary experiments in freezing oxygen and freezing methane, which we don't have a lot of database for, that might be a precursor to demonstrating that, hey, we can freeze cryogen and then ultimately we might be able to, like in this example, place boron atoms inside the solid hydrogen. And according to this analysis, preliminary analysis that was done by the Phillips lab, they believe they can get 90 seconds increase over oxygen hydrogen by just placing 5% boron atoms in the solid hydrogen. So that was really one of the reasons. The Air Force, because we have a very tight constraint on how we can physically manipulate atoms right now, when we can only get to this 5% level instead of the 15% level I was showing you for those more exotic launch vehicles using atomic hydrogen. If we can get that 5% level, gee, we may be able to do small incremental increases in propulsion rather than going by a factor of 50%. Maybe we can go up, instead of going 250 seconds, we can go up by maybe 80, 90, or maybe even 30 seconds.
You have some idea how to deliver this energy to a combustion chamber rather than having it come apart in the fuel tank here?
Sure. Yeah, we've done some analysis, and we're actually funded to do some experiments with solid hydrogen flow that will be flowing in a slurry of liquid helium. And one of the things that we've been doing, actually some analysis we did a couple of years ago, published in a paper, and it looks at how we might use very small pellets of solid hydrogen. And if I had more than 30 seconds, I bet you can find the chart.
Would adding boron to liquid hydrogen allow you to make the tank smaller on the X-33?
Could you repeat that question, please?
I heard it. It's a good question.
Repeat it, please, so they can understand.
Would adding boron to the liquid hydrogen tank on the X-33 allow you to get away with a smaller liquid hydrogen tank?
Okay, first of all, we couldn't use liquid hydrogen. We have to use solid hydrogen. And that would require a different type of heat system that we really don't have the expertise with yet. See, the kind of feed systems we've been talking about for these increases in specific impulse are particle feed systems, where we have clumps, if you will, or particles of solid hydrogen that have atoms built into them. And you can see the particle sizes we're talking about, and again, a reasonable line diameter, and this is centimeters. And we're here down around 10 centimeters or so is a particle size, 0.01 kilograms. So we've got relatively small particles. And this is typical of what is done in the fusion program. They have solid particles of hydrogen built with deuterium tritium, and they flow them into a reactor for a fusion reactor. So we're trying to take a jumping off point from the work that's already been done in the fusion program and say, hey, if they've done this kind of thing successfully at relatively low flow rates, maybe it will be attractive for a rocket system. And you can see here that this is not really a lot of flow rate. This is only like 10 particles a second. But if we had multiple of these lines all feeding into a combustion recombination chamber, then we might be able to get something reasonable in terms of our rocket system. Sorry.
Questions, please?
You mentioned that the Arctic was 607, 20,000 Kelvin. Why such a low specific impulse for 20,000 Kelvin?
Well, it's hydrazine as a propellant. It's not hydrogen. Hydrogen, theoretically, we can get about 900 to 1,000 seconds specific impulse with that very high temperature hydrogen. There are some material limits that we have to deal with, and also the satellite manufacturers like to use the same fuel as they've used previously. So it was a lot easier to sell and say, hey, if you can use the same hydrazine, all you have to do is add this arc jet and the power processing for it, and that will simplify the system. We didn't want to say, oh, yeah, by the way, you want to put this nitrogen tank, it's 3 times the size. And when you have it, it requires cryogenic storage and refrigerators and
If you only get 900 to 1,000 seconds, you get 900 to 1,000 seconds out of liquid hydrogen, just heating it up in a nervous dimension, leads it to a test dimension.
that's right, but you need, see the arc linkage passing it around the arc, so there's some thermal losses by having the hydrogen not in direct contact with the arc. Also, the nuclear thermal rocket is kind of unattractive politically.
Why not, I will get the problem, I'm not gonna do it.
Yeah, sure.
Bryan has really been a high profile long metal wireless speaker so far. And we're going to build on this a little bit. Bryan, we got your partner out there with the fuel tanks. You see Diane?
She's going to do a great job.
She's going to come in and put more propulsion into this. He's going from afterburner. I don't know where she's going to take off. She's really going. There's a tank that she's got to bring in. And rather than make her too nervous of bringing that around at 35 millimeters, if you'd like to talk to Bryan, we can tap into the hallway. And let you take a little break and let Diane get it. Her presentation is going to be manufacturing utilization of Mars and its sites of propellants. That'll be next.